Hello ladies and gentlemen, welcome to Oscillations tutorial. Let's take a look at question 1. Now for question 1, the main skill that we're going to learn is to be able to draw the graphs of displacement, time, velocity and acceleration time and derive the relevant equations for SHM just by reading the question. So let's take a look at the question. A particle is oscillating in SHM with period of 5 seconds, that's t, and an amplitude of 3 meters, that's x0. At time t equals to 0, the particle is at equilibrium position and moving to the right with right hand as positive. So the first thing we're going to do is to draw the displacement time graph based on the information given in the question. Now, so the displacement will be in meters and time in second. At time t equals to 0, the object is at the equilibrium point and is moving towards the right. This means that it's going to be a sine graph. The period is 5 seconds. So straight away, we also know that half the period is 2.5 seconds. And then 1/4 of a period will be 1.25 seconds. Okay, so this is going to help us in sketching the graph later, answering the question later. The maximum displacement is 3 meters and the displacement on the other side maximum is minus 3 meters. Now, once you have this, immediately what you can do is to write down the equation of the displacement. Then looking at the graph, straight away you can write the equation of the displacement is 3 sine 2 pi divided by 5 multiplied by t. Okay, so in this case, the frequency, we know that the period of the oscillation is 5 seconds. So the frequency of the oscillation will be 1 divided by 5. This is 0.20 hertz, okay? And the angular frequency, straight away, we can also say is 2 pi divided by 5, which when we work it out using a calculator will be 1.257 radians per second, all right? So we already have answered the first question, the frequency, and number 2, the angular frequency has also been answered. Now, let's take a look at what we can do next. What we can do next is to derive the velocity time graph straight away. Just looking at this, the first graph, the displacement time graph, we can go straight to the velocity time graph already. Now, how do we get the velocity time graph? The velocity time graph is by differentiating the displacement time graph. So when we differentiate a sine function, we're going to get a cosine function. Everything inside here remains the same, but the 2 pi over 5 will bring it out to the outside. So this will be 3 times 2 pi over 5. Now, what this means is that we're going to get a velocity time graph, okay, which is a cosine function. And the cosine function, just like the sine function on top, will have 5 seconds over here, 2.5 seconds over here, and 1.25 seconds over here. Okay, now, what is the maximum velocity though? The maximum velocity will be 3 multiplied by 2 pi over 5. So this will be the maximum velocity. Okay, I'm not sure why this keeps blinking. So if you work it out over here, the maximum velocity V0 will be equals to 3 multiplied by 2 pi over 5, which works out to be about 3.77 meters per second. So you can put down here 3.77 meters per second. Now, what we can do next is, of course, the next thing we can do is to get the acceleration time graph. And the acceleration time graph will just be a differentiation of the velocity time graph, right? So now the velocity is 3 times 2 pi over 5 cosine 2 pi over 5t. So we can get the acceleration by differentiating that. The cosine will differentiate into a negative sine graph with everything inside here remaining the same. All right, so what will happen is that the 2 pi over 5 will then go outside. So we get minus 3 multiplied by 2 pi over 5 bracket squared. Okay, so we can also work out the maximum value of the acceleration, which is modulus of 2 pi over 5 squared. And the maximum value of the acceleration will be 4.74 meters per second squared. So now we're going to have a negative sign graph with pretty much the same period as before. So this is 5, this is 2.5, this is 1.25, and the maximum acceleration will be 4.74 meters per second squared. Okay, so now we have all of the information here. We are now able to solve any of the questions that we want. Okay, so let's take a look at question 3. What is the displacement from equilibrium position at time t is equals to 1.00 second? So what we'll do is that to solve question 3, we will just use the displacement formula. X is equals to 3 sine bracket 2 pi divided by 5, and the time that they want is 1 second. And this works out to be equals to 2.85 or 2.86. Right? Now remember to use the radians modes on your calculator because otherwise the sine function will not turn out properly. Okay? Now let's take a look at question 4. What is the distance traveled from t equals to 0 to t equals to 1? Now, so that we know that when the time is equals to 1 second over here, this is 1.25 second. So 1.0 second is over here. So the object's displacement over here will be 2.85 meters. Okay, so it's 2.85. Now, this means that the distance traveled will be 2.85 meters, which is the same as the displacement. Now, let's take a look at question 5. What is the displacement when time is 2 seconds? Okay, so let's take a look at the graph. Now, when time is 2 seconds, it turns out that it's going to be somewhere over here, between 1.25 and 2.5. So let's fill in the equation again. X equals to 3 sine 2 pi divided by 5 multiplied by 2. This will give us the x position when the time is 2 seconds. So that's 1.76 meters. 1.76 meters. So at this point over here, this is 1.76 meters. Okay, 1.76 meters. So what about the distance traveled? So what is the distance traveled to 2 seconds? Now, how far did the object travel? The object went all the way to the right, 3 meters, then it came back to 1.76 meters. So this means that it went all the way to the right hand side and then it came back until now it's 1.76 meters position. So the distance traveled will be equals to 3 meters plus the little bit. When you go backwards from 3 to 1.76, the distance traveled is 3 minus 1.76. Okay, this is because the object, right, went from here, this is 3 meters, this is 0 meters, this is 1.76. It went from here to here, then it turned around and came back. Okay, so this means that the distance traveled will be 3 plus 3 minus 1.76, which is 4.24 meters. So this is 4.24 meters. Great. Let's take a look at question 7. What is the velocity at 1 second? So question 7 tells us the velocity at t equals to 1 will be equals to, and then we use the velocity formula over here. Okay, 3 multiplied by 2 pi divided by 5 times cosine 2 pi over 5 times 1. Okay. Now, we work out the number in a calculator and we get the v is equals to 1.16 meters per second. Now, the reason why it's to the right is because it's positive value. And we did say that any positive values are considered to be to the right. So you can see that over here, this is 1.16 meters per second to the right. Okay, so what is the velocity at 2 meters per second at 2 seconds? So the v at t equals to 2. Okay, so the v when t equals to 2 will be 3 multiplied by 2 pi divided by 5 cosine 2 pi over 5 multiplied by 2. Okay. And this gives us negative 3.05 meters per second, which means that it is to the left. Well, comment on your answer. The negative sign means that it is to the left. Okay, now let's take a look at question 9. What is the velocity at displacement 1 from the equilibrium position? So now, what is the velocity when the displacement is equals to 1? Okay, 1 meter. Now we'll use this equation, okay, plus minus omega square root of x naught squared minus x squared. Okay, so this would be plus minus 2 pi divided by 5 multiplied by square root of 3 squared minus 1 squared. So the number is 3.55 meters per second. Now we need to figure out whether it's to the right or to the left. Okay, so let's compare the possibilities. Okay, so now when is the displacement 1 meter from the equilibrium position? Okay, so you know that the maximum amplitude here, the maximum displacement is 3, right? So this means that it can be, the object could be either moving in the positive direction, that means it's going upwards, or it could be moving in the negative direction, that means it could be moving downwards. Okay, so there's two possible timings at which the displacement could be 1 meter. All right, so this means that the velocity at when the displacement is 1 meter could be plus minus 3.55 meters per second. That means it's to the right or to the left. Okay, so at the displacement 1 meter, it could be either moving to the right at 1 meter or moving to the left at 1 meter. Now let's take a look at question 10. What is the displacement at what is the velocity at displacement minus 1 meter from equilibrium position moving to the right? Okay, so let's try again. Over here, the velocity at the displacement of minus 1 meter moving to the right. And if we put down the formula, we'll find that actually moving to the right will be the positive value, okay? And the formula is pretty much unchanged. Okay, so that will be plus 2 pi over 5 multiplied by 3 squared minus 1 squared, which is basically the same thing, positive 3.55 meters per second to the right. Okay, let's take a look at what's the next question. What's the velocity at displacement minus 2 meters from equilibrium position moving to the left? Okay, so once again, we'll fill in the formula. What is the velocity at minus 2 meters position moving to the left? So this will be the negative value of omega x naught squared minus x squared. So this will be minus 2 pi over 5 square root of 3 squared minus 2 squared. Okay, and that gives us a negative 2.81 meters per second squared. Sorry, meters per second. And the last question of this very, very long question is what is the acceleration at displacement minus 2 from equilibrium position moving to the left? Okay, all right. So let's take a look at the acceleration formula. Okay, the acceleration formula that we can use is A is equals to minus omega squared x. So when A at x is minus 2 meters, right, it will be minus 2 pi over 5 squared multiplied by minus 2. And this gives us a value of positive 3.16 meters per second squared to the right. Now we know that it's to the right because the value is positive, and also because when the object is on the left, the acceleration will always point towards the center of the equilibrium position, so it will always point to the right. Okay, so this is the answers for questions 3 through to question 12. And you realize that all these questions are easy to do because we know how to draw the graph of displacement, velocity, and acceleration time. Okay, so this is the end of question 1. Okay, let's take a look at question B, part 1. Sketch the displacement time graph for one cycle. Well, we've already done that when we first looked at the question. Okay, mark on the graph the points C and E for A3 and A5 respectively. Now, A3 is when the displacement is equals to 1 meter. When the time is equals to 1 second, sorry. And A5 is when the time is equals to 2 seconds. So how do we mark that down? Is because we know that the midpoint of the cycle is 2.5 seconds. And 1/4 of the cycle is 1.25 seconds. So 1 second is somewhere over here, and 2 seconds is somewhere over here. Now use the graph to determine direction of velocity at C and E. Now, how do we determine the direction of the velocity? You see, time will pass to the right. So as time passes, all right, the object is going to move along this curve and then down again. So what happens is that at point C, you can see that the object is going to go up the curve again. Now, positive displacements are considered to the right and negative displacements are considered to the left. So this is right and this is left. So at point C is moving right. And at point E, it's going to be moving left. Okay, so this is going towards the center point again. All right, now let's take a look at part C, part 1. Sketch the velocity displacement graph for one cycle and find the maximum speed. We've already done this. Find the maximum speed. Okay, so here is the object, here is to the right, and here is to the left. So when the object is moving here, it's going to be very fast. And then when it reaches here, it's going to stop for a while, and then it's going to go back, okay, and it's going to go very fast again. And then it's going to stop for a while over here, stop, and then it's going to go fast again. So let's take a look at how we're going to draw the displacement velocity displacement curve for this. Now the object goes right by 3 meters over here, and then it goes to the left. This is minus 3 meters over here, minus 3 meters. So when it's in the center, the velocity is very fast. How fast is fast? Well, 3 times 2 pi over 5. Okay, that was what we figured out just now. That 3.2 pi over 5 is kind of like 3.78 meters per second. Okay, this is the velocity in meters per second. Then when it reaches the end, it's going to be very slow. Okay, so it stops. Then when it comes back on the other side, it's going to be very fast again, minus 3.78 meters per second. Then when it reaches the end, it will be slow again. So this is how it moves. It goes fast to the middle point, then it slows down, hits the end, then it goes fast, but in the opposite direction to the middle point, and then it goes slow again. Now the equation for this graph will be v equals to plus minus omega square root of x naught squared minus x squared. This is the graph of an ellipse. This is the graph equation of an ellipse. Okay. Mark on the graph the points A and B for time t equals to 0. So this is A, and time 1.25 seconds respectively. Okay, so at 1.25 seconds, the object will be at the maximum displacement. Okay, mark on the point J and K for A10 and A11 respectively. Okay, let's try to remember what is A10 and A11. A10 is when the velocity is at displacement minus 1 meter from the equilibrium position moving to the right. So this is A10, and the velocity of displacement minus 2 meters moving to the left. This is A11. Okay, so let's take a look at the graph over here. So this is going to be A10, and this one is going to be A11. All right, so that means that A10 will probably be somewhere around here. Okay, this is A10 or J, A10. And this is probably going to be A11. A11 is K. Okay, all right, so this is how the object will move left and right. Now let's take a look at part D. Sketch on the particle acceleration displacement graph for one cycle. Okay, the acceleration displacement graph, AX, follows the equation A is minus omega squared x. So this is going to be a straight line graph through the origin. The maximum value, of course, is 3 meters on the right and negative 3 meters on the left. The maximum displacement will be this given by this. The maximum displacement A naught is equals to 2 pi over 5 squared multiplied by the maximum displacement, which is 3. Okay, and that will be 4.76 meters per second on the top and negative 4.76 meters per second on the bottom. Now mark on the graph the point L for A12. For A12, right, the acceleration at displacement negative 2 meters from equilibrium position and moving to the left. So if first we put down a negative 2 meters displacement, then we can find the acceleration on the point here. Okay, you can see that when the displacement is negative, the acceleration is positive over here. So that means the acceleration will be towards the right. That's all for question 1D. Now let's take a look at question 2. A particle is oscillating in simple harmonic motion between the points A and B, where OA and OB is 2 meters. At time t equals to 0, the particle is at O and moving to the right. Take right as positive. So the first thing we should do is to draw the displacement time graph. Okay, so this is the displacement time graph. Luckily, everything's in seconds and meters. How convenient. Okay, when time t equals to 0, the object is at the equilibrium position and moving to the right. So this is the, the displacement time graph, very simple. Now, when it reaches point A, which is at the extreme position over here, 2 meters, this is point A, the time is 1 second. So clearly, this will be 2 seconds, this will be 3 seconds, and this will be 4 seconds. So the amplitude is 2 meters is correct, is true. The period is 4 seconds is also true. Let's find out what is the angular frequency of this motion. The equation for this motion will be x is equals to 2 sine 2 pi divided by the period multiplied by time. So the angular frequency will be the thing that's in front of the t, which is 2 pi over 4, which basically will be pi divided by 2, 1.57 radians per second. So that is true as well. Okay, u is distance over time. So at time t, the particle is O and moving to the right with speed u. So can we use this formula? V when x equals to 0 is equals to distance divided by time, 2 divided by 1. This is not true. This is false. How come? Because velocity is given by the equation 2. Okay, differentiate the, you're going to differentiate the displacement, okay? 2 pi divided by 4 cosine 2 pi over 4t. Now, so when the object is at the center, when time t equals to 0, at velocity when time t equals to 0, will be 2 times 2 pi over 4 cosine of 0, which is going to give us 3.14 meters per second. So this is the correct answer. All right, not 2. Yes, 2 is like you can't use distance over time for this. Okay, after finding u, we can calculate the acceleration using s is equals to ut plus half at squared. Of course, this is not true. Okay, because for the acceleration formula, we have to use this formula 2 pi over 4 squared sine 2 pi over 4 t. Or you can use the acceleration formula a is minus omega squared x. This formula is with t, with respect to t, and this formula is respect to displacement. Okay, so this is false and this is false. What about point P? Point P is between O and A, where PA is 0.5 meters. Ooh, PA is 0.5. This is very scary. Okay, so PA is 0.5 meters, means it's over here. P is over here. This is 0.5. Now, OP is 1.5. Okay, so this distance here is 1.5, and this distance here is 0.5. So it says that to find the time taken from P to A, we use x is equals to x naught sine omega t. So this is what the question says. So I put 0.5 is equals to 2 sine 2 pi over 4t. Is this true or false? Now this is definitely false because this is the distance PA. The distance PA, all right, this is O, this is A, this is P. The distance PA is 0.5, but that's not the displacement. The displacement is measured here. This is the displacement XOP, okay? So actually it should be, this is wrong. This is wrong. The correct answer should be using 1.5 is equals to 2 sine 2 pi over 4t. Okay, so don't use the wrong side for the displacement. Right, so that's question 2. Now let's take a look at question 3. The displacement time graph for a body performing SHM is as follows. At which point is the velocity 0, acceleration 0, the speed maximum, acceleration maximum? Okay, the velocity and acceleration in the same direction and the velocity and acceleration opposite direction. So let's take a look at how an object might move in simple harmonic motion. Okay, so here is an object, okay, and then it goes to the right, and then this is where it ends up, then it goes to the left, then it goes to the left, then it goes to the right again. Okay, so this is how the object will move in a simple harmonic motion, left, right, left, right. Okay, so this is the object at point A. Okay, this object is point A. At point B, the object is over here. At point C, the object is over here. At point D, the object is over here. At point E, the object is over here. At point F, at point G, and at point H. Okay, so at which points is the object velocity 0? Well, the velocity is 0 at these 2 points, C and G, because that's where the ends of the motion are. At which point is the acceleration 0? The acceleration is 0 at the center point, A and E. Now that's because the acceleration always tries to bring the object back to equilibrium. The acceleration is always pointed towards equilibrium position. So when the object is at the equilibrium position, equilibrium means that there is no acceleration. So the acceleration is 0 at equilibrium position. So A and E is 0. Now, where is the acceleration maximum? The acceleration is maximum at the ends, C and G. Okay, so the velocity is 0 here, velocity 0. Over here, the velocity 0. Over here, the acceleration 0, velocity max. Over here, the acceleration max, velocity 0, acceleration max. Okay, so you can see that at the ends, the velocity is 0, acceleration is max. Then in the center, the velocity is max, but the acceleration is 0. Then it goes over to the other side. Okay, in which points are the velocity and acceleration in the same direction? Let's take a look at point H. At point H, the velocity is going right. The acceleration is also going right because the acceleration always points towards the equilibrium position. Okay, at point B, the velocity is going right, but the acceleration is going left. At point D, the velocity is going this way, and the acceleration is going this way. Then at point F, the velocity is going this way, but the acceleration is going this way. So when are the velocity and acceleration in the same direction? In the same direction, this will be point D and point H. Now, when is the velocity and acceleration in opposite direction? The velocity and acceleration is opposite direction at point B and point F. Okay, So I hope that helps you to explain the answer. Now, I tend not to use graphs when I want to find out the direction, because I always get messed up about, positive and negative signs. So for me, oscillations is a very physical subject. So when things move, I also move. Okay? Now let's take a look at question 4. The rise and fall of water in a harbor is simple harmonic. The depth varies between 1 and 3 meters. What is the earliest time that the water is 1.5 meters deep? Okay, so let's take a look at this graph here. This graph is not a SHM because the equilibrium point is not 0. Okay, so this is not a cosine graph at all. Now what we need to do is to find the equilibrium point over here. Then we can turn it into a cosine graph. And the equilibrium point is at 2 meters depth. So now we shift the whole graph downwards by 2 meters, okay? So we don't call it depth, we can call it delta D, all right? The change in the depth. So the change in the depth looks like this, okay? So now it's 0, and then at the bottom is -1, and the top is +1 meters. Because basically the tide goes up by 1 meter, and the tide goes down by 1 meter. So now we can draw the equation. This is going to be a cosine graph, yeah? Cosine graph, negative cosine graph, in fact. So it's -1 cosine of 2 pi divided by, what's the period? So 5 a.m. here, time needs to be start from 0, yeah? So 5 a.m. to 5 p.m., that means this time is 12 hours. So it's 12 hours. So we put down here time in hours, this is 12, okay? So it's 2 pi over 12 multiplied by t. Okay, so this is the equation for our graph. Now, the first low tide is at 5 a.m. What is the earliest time that the water is 1.5 meters deep? So where is 1.5 meters deep? Now, 1.5 meters deep is this depth. So they want us to find what time is it over here? Time. Okay, time. So this 1.5 meters means that it's down by 0.5. So the displacement here that they want is actually minus 0.5 meters, and this is the time that they want. So what is the time when the depth is 0.5? When the depth is minus 0.5. Wait, what am I doing? Okay, so we put minus 0.5, that's the depth, is -1 cosine 2 pi over 12 t. Now, using a graphic calculator, it's easy to solve for t. And we obtain here t is equals to 2. But does that mean that it's 2 a.m.? It's not 2 a.m. So the time is 5 a.m. plus 2 hours, which is 7 a.m. Okay, so the earliest time that the water is 1.5 meters deep will be at 7 a.m. Now let's move on. What is the next earliest time that the water is 1.5 meter deep? Now, by symmetry, okay, by symmetry, right? If this time period here is 2 hours, then by symmetry, this time period here is also 2 hours, also 2 hours. So the next time that the height of tide will be 1.5 meters will be 5 p.m. minus 2 hours. So that will be 5 p.m. minus 2 hours. That will be 3 p.m. Okay, so the high tide will occur at 7 a.m. and 3 p.m. That's the end for questions 1 through 4.